Hello everyone, welcome back to my channel. In this episode, I'm going to talk about PID control. I won't bore you with complex concepts. Let's use a simple example to illustrate this. This is the mass of a vehicle, and this is the suspension stiffness K, and this is the suspension damping coefficient C. And we add a variable force F, which we will use PID to control it. So this is the tire, and this is the road disturbance. Alright, so the road disturbance displacement is Z0, and the mass displacement is Z. So what is PID control? This is time, this is Z. Let's say this. The Z looks like this. Alright? So this is not comfortable for the driver and the passengers. Let's assume our target of Z is a straight line like this. We call it ZD. So the arrow equals between ZD and Z. It's the arrow E. Here, this is our target ZD minus Z. Generate the arrow E. So the PID control, it only has one core mission: to eliminate the arrow E. This is PID control, generate a force F to eliminate the arrow E. Alright, let's build the motion equation. The motion equation goes to m times z double dot. This is the vertical acceleration of m equals the suspension stiffness K times the relative displacement between Z0 and Z. Then the damping coefficient C times the relative speed Z0 and Z dot. Alright, finally, plus the variable force F. This is the motion equation of this model. Then we build the control system. First, for the arrow E equals ZD minus Z. Then the input of the force U equals, this is the K point of this episode. The PID control equations goes to, first, the P for proportional Kp times the arrow E plus I, this is integral Ki times the integral from O to T E tau d tau, and D derivative plus Kd times E tau dot. Alright, this is the PID control equation. It looks very simple. It consists from the proportional Kp and integral and derivative. Then its purpose is to eliminate the arrow E. So the force goes to the gain times the input U. Alright, this three equation, we call it the control equation. Then, in order to make it easy to build the model in Simulink, let's change the form of the first equation. So Z double dot equals k over m times z0 plus, let's put the z0 and z0 dot together, c over m times z0 dot minus k over m times z plus c over m times z dot plus f over m. Alright. With these four equations, we can build a model in MATLAB and Simulink. Then we can see how does these three coefficients work. Alright, let's set values for each parameter in MATLAB. The m equals 100 kilogram, and suspension stiffness is 100 Newton per meter. And the suspension damping coefficient is 5 Newton second per meter. And the actuator gain is 100. The PID control coefficients, we set the inertia value as 0. Kp, Ki, and Kd are all 0. And this is the road disturbance. Alright, let's run it. All the values are stored in MATLAB. And here type Simulink. Let's build a model in Simulink. Alright, in the Simulink, first type Inport and click Model Settings. In the Date Import, let's import the road disturbance. The road disturbance is input data structure. Okay. Let's see the displacement of the road disturbance. Let's type here scope. Link to the scope and run it. Alright, double click scope. This is the road disturbance we'll set. Alright, delete the scope. This is the motion equation we just built. First, let's build the z double dot. And z0 is import 1, the road disturbance. And the k over m is gain. So here type gain. Double click it. And this is k over m. Enlarge it. Link to it. This is the first term. The second term, the 0 dot. So here type derivative. Link to the 0. This is the 0 dot. The gain is c over m. Type here gain c over m. Link to it. Oh, the big letter C. All right. So sum these two terms together. Type sum. Double click it. let's change the vertical to the end and the plus vertical. All right. Link to the sum and link to this term. The output here, this is the Z0 two terms. And we're going to sum with 1, 2, 3. Totally 4 terms together. So here, type add. Double click it. We have 4 terms, plus. So link the Z0 two terms to the second. And we're going to add the Z terms. And here the output. This is Z double dot. So we need a integrator and the second integrator. So Z double dot combined by 2 integrator, we get Z. And for the Z terms, first Z over M times Z. Let's type again and Control I, change the direction. This side to the Z. Oh, let's change the gain value, K over M. All right, this should be minus. Enlarge it. Link to the add. And the next is Z dot terms. Here, type scan, Control I, change the direction, double click, minus C over M. This is Z dot and link to the add. All right, now we finish this equation, but we still need F in this position. So let's build the control equation model. For the control equation model, first we need to define the ZD, our target. As we talked before, as we said before, the ZD is a straight line, so type constant. Let's change the value. The value 0.005. Let's set the target as a straight line 0.005. Then we type sum and let's change the value to let's change the symbol to minus. So link here and link to the Z. So the output is ZD minus Z, the arrow. All right. Next, for the input U equation. First is the PID P, proportional. Again, our proportional KP. Link here. Then we build the integral terms. This is the integral of the arrow E. So here, integrator from the arrow E and the gain K I. All right. The third terms is KD, derivative. So here is the derivative. Link to the arrow E and the gain. The gain is KD. All right. And sum them together. Here's add. Link to the add. The output here is input U, and we add again for the actuator. The gain is G. The output is our variable control force F. All right. The last step, F over M to the Z. So we add a gain here. This is 1 over M. And link this value to here. All right. We finished our model. And let's see the result. First, let me close the picture. And we want to compare the input of the road disturbance and the Z and also our target. So milks, double click the input are 3, enlarge it. First, this is the target. Double click here. This is Z, D, our target. And this is Z. Move it to here. And this is the road disturbance. Z0. Z0. Move it to here. And type here scope. All right. Let's run it. This is the simulation result. As you can see, the red line is the road disturbance, and the blue line is mass M displacement, Z, and the yellow line is our target. Let's look at these simulation curves to see exactly what the 3 parameters of PID control are doing in real time. Return to the MATLAB. As you can see, all the parameters of PID control are 0. First, let's increase the value of P proportional from 0 to 2. Right? And refresh the simulation. Look at the screen. The blue actual curve which was originally way off, is immediately pulled right up near the yellow target line. The role of P is to fight the current arrow. Think of it like a spring in a car suspension. The further you deviate from your target, the harder it pulls you back. But a pure spring has a problem. It has no damping, which leads to this severe oscillation. To fix this bouncing, we bring in D, derivative, and set its value to 2.5. Right? Refresh the result. Watch the curve now. That violent jumping is instantly flattened out. D acts as a shock absorber. It hits the brakes and efficiently dampens the vibrations. The blue line is stable now, but there is still a gap between it and the yellow target line. This is called the steady state error. So, how do we close the final gap? We add I, integral, and set its value to 2. Right? Refresh the result. Just like magic, the blue line now is almost perfectly hugs the yellow target line. The role of I is to be relentless. It fights until the very end to completely wipe out that steady state error. That is teamwork of PID. However, PID control does have its limitations, which I will explain in detail in the next video. See you next time.